Good morning, good afternoon, and good evening, everyone. Welcome to today's Ask the Expert webinar on vibrational spectroscopy for materials analysis. Our experts for today are Yannicka Schneider, Senior Scientist and Project Manager, Wensheng Tang, Manager Organic Analytical Services, and Victor Orr, FTIR Scientist. My name is Rena Samsu, and I am the Senior Marketing Manager assisting with today's event. Before we get started, let's go over a few housekeeping items. All attendees have been muted. However, if you have additional questions that pop up during the presentation, please submit them in the questions section located in the bottom of your control panel. You may send in your questions at any time during the presentation. Time permitting, we will answer these questions during today's event, or we will follow up with you in the coming week. With the abundance of pre-submitted questions for today's event, we unfortunately will not be able to get to all questions during the presentation. For any unanswered questions, the team will send answers out to those questions soon. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to one of our experts for today, Yannicka Schneider, who will also be moderating today's presentation. Yannicka?
Thank you, Rena. Welcome everybody to our Ask the Expert webinar focused on vibrational spectroscopy for materials analysis. So first, I would like to introduce our presenters today. So my name is Yannicka Schneider. I will be the moderator. And I have been at EAG for about 10 years. I have more than 20 years of experience in materials characterization, and I specialize in FTIR and XRF spectroscopies. I'm also a project manager, so I manage complex projects involving multiple techniques. Wensheng?
All right. Hi, everyone. My name is Wensheng Tang. I'm the manager of the Organic Analysis Group here at EAG. I have been with EAG for over 8 years, and I have over 10 years of experience working in material characterization, as well as vibrational spectroscopy. At EAG, I specialize in FTIR and Raman analysis. Thank you. Victor?
Hi, everyone. My name is Victor. I've been at EAG for over 1.5 years now, and my background is mostly in NanoIR, and I've around 6+ years in that in FTIR.
Wonderful. Thank you, everybody. Okay. So now for today's agenda, we're going to start with a brief introduction to EAG, what we're all about. Then we'll talk about our famous smart chart. And of course, the bulk of this presentation is focused on your questions. You submitted more than 400 questions, and of course, we're not going to cover everything, but we're going to sort of go into the most interesting ones, and all your questions will be answered, rest assured. So we'll start with vibrational spectroscopy, FTIR, Raman, NanoIR, and if we have time, we'll have your questions from today, and we'll end with a brief summary. So who is EAG? EAG is part of the Eurofins family, which is a leader in global testing. Eurofins EAG specializes in materials testing. We're a large company. We have more than 1,000 employees, more than 5,000 different clients. We have labs all over the world, as you can see, at 20 different locations, and we're a leader in materials testing. And we work with our clients during the entire life cycle of products. So from R&D and investigation of new materials to quality control to failure analysis, and we even offer litigation support. Okay, so now I'm going to talk briefly about vibrational spectroscopy. So what is vibrational spectroscopy? Exactly, we received a lot of questions asking us to explain what is FTIR and Raman and how do they work? How is vibrational spectroscopy used for material analysis? What is the best material to analyze with one versus another technique? So the bulk of our presentation is going to focus on that, but let's just basically break down vibrational spectroscopy. It's very simply an interaction of electromagnetic radiation with matter. So we're shining a light at a sample, and we're obtaining a spectrum, basically a fingerprint that tells us about the material's composition. And how does this work exactly? So when you shine a specific kind of light at an organic molecule, such as this carbon hydrogen molecule, it can experience a variety of vibrations. So for example, it can have a symmetrical vibration, such as symmetrical stretching, asymmetrical stretching, as well as the scissoring vibration. And these vibrations occur at different frequencies. That depends on the atom and the bonding next to that atom. And in this manner, you can basically, you get a fingerprint of the material. Now, the difference between the three main techniques we're going to discuss today is related to the excitation source and the signal that is detected. So with FTIR, we're using infrared light, and we're detecting the transmitted or reflected light. With Raman, we're using near-IR visible or UV light from a monochromatic laser, and we're measuring the scattered light. And with NanoIR, we're using a tunable infrared laser, and we're measuring the deflection of the AFM cantilever. All right, so now let's talk about our smart chart. This is a very useful tool for understanding detection limit, spot size, and so we call it the Spectroscopy Microscopy Analytical Resolution Tool. So what you can see here on the x-axis, we have the analytical spot size ranging from 0.1 nanometers to 1 centimeter, and then we have the detection limit from percents down to parts per trillion. So now let's take a look at our three techniques. So FTIR, as you can see, it has a detection limit or a spot size that it ranges from millimeters down to maybe about 20 microns. And the detection limit is in the percent. So you can see this technique has some of the lower detection limits, a worse detection limit compared to something like dynamic SIMS. And then Raman, you could see, has a much smaller spot size, down to 1 micron, and has a similar detection limit to FTIR. And NanoIR, this one has the smallest spot size. It can go down to 30 nanometers. But again, the detection limit is similar to all the other techniques. Okay, so now what about depth? When we introduce the third dimension into our material. And so with NanoIR, we can probe down to hundreds of nanometers. With Raman, it can be down about a micron, but you can also do confocal, so you can go further into the sample. And with FTIR, it's really a range from tens of nanometers down to 1 micron or several microns. Okay, so again, a lot of questions came in about detection limit and resolution. So we put together this chart for you comparing the three techniques. So as mentioned earlier, the analytical spot size with FTIR with the microscope, you can achieve about 20 microns to about 100 microns. And then with different accessories, you can do, millimeters spot size. For Raman, it's about 1 micron. And for NanoIR, it's 30 nanometers. With respect to the detection limit, this is where we say 5 to 28%. This is because, especially in a mixture, you really have to have a considerable concentration of the analyte present to detect it. So this technique is not going to detect trace level, percent level species unless they are very strong Raman or IR absorbers. And there are some molecules, like for Raman, carbon is detected at very trace level, but in general, this is the detection limit. So this is not a sensitive technique for trace analysis. Spectral range, FTIR has the highest spectral range, about 6,000 to 400 wave number. Now that 400 is achieved with a special accessory. And Raman, 3,500 to 50 wave number. NanoIR, 760 to 1,800, and 2,700 to 4,000. This is laser dependent, so we're listing here what our instrument is capable of doing. And finally, the depth of information. With a special accessory, you can achieve 50 to 100 nanometer depth, and then 2 microns with the diamond ATR. For Raman, the depth is 1 to about 10 microns, NanoIR 30 nanometers to a micron. And we received some really good questions about, you know, what is a trade-off between spot size and sensitivity? So great question. So when you're going to focus your microscope on a very small area, you're going to sacrifice sensitivity. So there is certainly a trade-off. And the thicker the sample for microscopy, the better the signal typically. Okay. All right, and so I'll briefly talk about applications of vibrational spectroscopy. We received a lot of questions, you know, is this going to work for package product interactions, to test medical device raw materials, for nanofiber tissue scaffolding, or and the answer is yes. It will work for most organic molecules. Any kind of organic molecule should that has a rich IR Raman spectrum, it should work well. So we can look at particles, fibers, films. This is a very, very useful tool for contamination analysis, especially of unknown materials. And you can use it to look at cleanliness and so on. These are the typical applications. There are some very specialized applications, such as determining polymer cure with FTIR or Raman. You can do quantification of oxygen, hydrogen, silicon wafers, or a quantification of hydrogen, silicon nitride wafers. And these are wonderful for semiconductor applications. And I will end my portion by just saying these techniques are really can be used for a variety of industries. They are not industry specific. And so we'll talk about different applications in just a few minutes, but suffice it to say, any application you can think of that has organic molecules can benefit from these techniques. Okay, and now I will hand it over to Wenchong, talk about FTIR and Raman.
All right, thank you, Annika, for the general introduction to vibrational spectroscopy. Now I'm going to move on to discussions that are more specific for FTIR and Raman. So as you can see, we received many questions asking about how FTIR and Raman work. So the working principles behind the two techniques are actually quite different. In FTIR analysis, a broadband infrared light is utilized as the excitation source. When the sample is illuminated by infrared light, the molecules get excited from the ground state to the vibrationally excited state through the absorption of a photon. Not all photons get absorbed equally. Only the ones with energy matching the frequency of the molecular vibration gets absorbed, resulting in an absorption spectrum that reveals the molecular structure of the sample. In Raman analysis, it is quite different in that a monochromatic laser was utilized as the excitation source. The laser has much higher energy compared to the infrared light. So after absorption of the photon, the molecule gets excited to a high energy state, which is quite unstable. A small portion of the molecule from this high energy state would lose energy, fall back down to a vibrationally excited state through the emission of a photon with different energy compared to the incident photon. This frequency shift in the scatter photon compared to the incident photon is what we call the Raman shift, which carries important information regarding the molecular structure of the samples. So by comparison, it is clear to see that FTIR is based on light absorption, whereas Raman is based on light scattering. So aside from the working principles, another very important concept in FTIR and Raman is the selection rules. So we received questions asking how to determine if a vibration is IR or Raman active, or do all the bonds get detected equally? So both of those questions can be answered using the selection rules. The selection rules state that molecular vibrations that are IR active must be accompanied by a change in dipole moment, whereas the Raman active vibrations are accompanied by a change in polarizability. Due to the differences in selection rules, some compounds or molecules that have a strong response in FTIR may produce a weak response in Raman and vice versa. So taking water as an example, due to the presence of a permanent dipole moment, water produces very strong absorption in FTIR analysis, and that is why FTIR is preferred to be performed in a nitrogen-purged environment. Raman, on the other hand, is not sensitive to moisture. This is because water is a very weak Raman scatter, so in a lot of cases, it is very challenging for Raman to even detect it. Another example I have here is a compound called ethyl acrylate with its structure shown here. So in the FTIR spectrum of this compound, the most intense peak is produced by the vibration of the carbonyl group, whereas the acrylate double bond produces very weak absorption in FTIR. This trend has been reversed in Raman, where the most intense peak is produced by the vibration of the double bond. So this is because the pi electrons in the double bond are highly polarizable, making them a very strong Raman scatter. In general, the differences in selection rules makes FTIR and Raman complementary techniques in material analysis. So now moving on to instrumentation, we received questions asking the manufacturer as well as the configuration of our instrument. Our FTIR comes from Thermal. It contains a FTIR microscope, built-in diamond ATR, as well as a bench spectrometer that can be coupled to different types of accessories. We do not have a TGA that is connected to our instrument, but we do have a TGIR available in our Syracuse lab. Our Raman instrument comes from Horiba. What is really unique with our instrument is that it is equipped with 5 different lasers as the excitation source. The laser wavelength covers the UV, visible, and then to the near infrared region. The wide selection of the lasers gives us the ability to achieve optimized analysis for a wide range of materials. So FTIR analysis can be performed in different modes, and we received questions asking for explanation of those different modes, as well as if there's a preference among them. So in general, there are 3 commonly used analysis modes in FTIR analysis, including transmission, reflection, and ATR. So transmission analysis is what we use most frequently in our lab. In transmission analysis, the material of interest needs to be transferred onto a IR transmissive substrate. The sample needs to be sent out to proper signals to allow the transmitted light to be detected. Since the transmission requires sample preparation, the minimum sample size requirement is typically around 100 micron. And since a small portion of the material needs to be removed from the original sample, transmission analysis is destructive to a certain extent. If the material of interest is located on a light reflective substrate, such as a metal, then analysis can be performed in situ in the reflection mode. Reflection analysis doesn't require sample preparation, so it is fully non-destructive, and the minimum sample size requirement can be reduced to around 20 micron. Lastly, we have the ATR analysis mode, which is a very popular mode in FTIR analysis. ATR is the surface-sensitive mode in FTIR analysis, where it involves the use of an ATR crystal made of high refractive index materials such as diamond or germanium. The ATR crystal helps to confine the penetration depth of the infrared light, typically to around 1 to 2 microns from the sample surface. By using a grazing angle ATR attachment, the penetration depth can be further reduced to around 100 nanometer or less. So this relatively high surface sensitivity in ATR mode makes it a very useful tool to characterize some films or coatings or surface layers in multi-stack structures. With the use of the microscope, the spot size for ATR analysis goes down to around 50 micron. ATR doesn't require sample prep, so it is non-destructive. One limitation with ATR analysis, though, is it requires the sample to have a flat and smooth surface, or the sample has to be flexible so that an intimate contact between the crystal and the sample can be obtained, which is crucial for successful ATR analysis. So when given a certain type of sample, we really need to take into consideration such as the purpose of the analysis, the geometry, the size, or even the texture of the sample in order to choose the most appropriate analysis mode to characterize it. Moving on to the questions for the samples, we got asked what type of bonds or what type of material is most suitable for FTIR and Raman analysis, or can those techniques be utilized to identify inorganic materials? So here I have this table which can be used as a general guidance to determine the feasibility of FTIR and Raman for analyzing different categories of materials. Generally speaking, both FTIR and Raman are powerful tools to characterize small organic molecules as well as polymers. For metals, unfortunately, it cannot be detected by either technique because metals are not active in FTIR or Raman analysis. Inorganics can get a little bit tricky. In general, FTIR has very limited capability for inorganic analysis. FTIR detects inorganic carbonates, nitrates, sulfates, and silicates, but a lot of the times it is very difficult to use FTIR to differentiate them. Here I have an example of the spectrum for inorganic silicate and the inorganic sulfate. As you can see, those two types of compounds produce very broad absorption features in a very similar spectrum range, making them very difficult to be differentiated using FTIR. Raman, on the other hand, has much better capability for inorganic analysis, and it works extremely well for crystalline materials. Here I have an example showing the Raman spectrum from different types of iron oxide compounds. Each type of compound produces distinct features in their Raman spectrum, making them easily distinguishable by Raman. And even for the iron oxide with the same composition, if they come in different crystalline forms, they can still be readily differentiated using this technique. Another category of material that benefits from Raman analysis are elemental species, such as elemental carbon. This should not be interpreted as Raman detects element. In elemental carbon, for example, it is the sp2 and sp3 carbon-carbon bond that gets detected by Raman, not the carbon elements. So very important note here. FTIR and Raman detect chemical bonds and functional groups, not the elements. So now let's switch topic and take a look at questions on data interpretation. The majority of the questions that we received ask us, what type of libraries or databases do you recommend that can be used for spectrum interpretation. So here at EAG, we have the most extensive FTIR and Raman libraries, including a subscription to the widely known all libraries, the libraries provided by the instrument vendors, as well as a user-developed library that is proprietary to EAG. This adds up to a total of 350,000 FTIR reference spectrum, as well as around 30,000 Raman spectrum. For people who do not have access to commercial libraries, the frequency tables that are readily available online can be a very useful tool to assist with spectrum interpretation. Additionally, there were two open source libraries online that I want to mention, and I know most people are probably not aware of. One is called the NIST webbook, which contains a good number of FTIR spectrum for small organic molecules. There's also a database called RROF database, which contains a good number of Raman spectrum for a variety of mineral materials. So both of those two databases offer the reference spectrum in a downloadable format. So I highly recommend that you go ahead and check them out. Another popular question we received regarding data analysis is, how can you perform spectrum interpretation for new materials or for complex mixtures? Mixture analysis can become quite challenging, but at the same time, it's something we have extensive expertise with at EAG. So here I have a list of the general approaches that we typically apply to perform mixture analysis. And using this mixture spectrum as the example, I'm gonna walk you through the typical process. So when we were given a unknown of a mixture spectrum, the first thing we would do is to throw the spectrum into the library and check to see if there are any good matches. So take a look at the reference compounds in the hit list. Overlay the reference spectrum of those compounds with your unknown spectrum, check the match, and then try to account for as many peaks as possible. It is quite often to find peaks as highlighted here that cannot be accounted for using the compounds from the hit list. What one can do next is to confine the library search to just those highlighted peaks. By doing this, we can get a new hit list with different reference compounds from the library, or alternatively, we can do a spectrum subtraction by removing the peaks from the known materials and then get this subtraction results. Search the subtraction spectrum in the library again. In this case, we actually get a very similar hit list compared to the highlighted region search. So by doing either method, and then check the matches against the different compounds in the hit list, we were able to clearly identify that those highlighted peaks can be assigned to a aliphatic amide compound. And speaking of spectrum subtraction, we received a question asking about the negative peaks or arbitrary peaks in the subtraction results. Those artifacts can be generated by many different factors, and unfortunately, it is not possible to fully avoid them. Nonetheless, the spectrum subtraction results still can be a very useful tool when it comes to spectrum interpretation. So now back to this mixture example. By performing both library search and spectrum subtraction, we were able to definitively identify the three individual components in this mixture. For more complex mixtures, one may need to go back and forth between those steps and repeat this process multiple times. But in general, the combination of library search and spectrum subtraction gives us a very effective protocol for mixture or unknown analysis. And for people who do not have access to commercial libraries, I recommend to perform a functional group analysis on the spectrum. Although it would be very challenging to pinpoint to specific compounds by doing just functional group analysis, one can still get an educated speculation on the general categories of material that may be present in your sample by assigning the functional groups to major peaks and then take a look at the different combinations of those functional groups. Last but not least, literature search can be a very useful tool, especially for assigning unknown peaks in new materials. So definitely do not forget about that. Now moving on to case studies. So in the next couple of slides, I have a few examples highlighting the capabilities of FTIR and Raman for a couple specific applications. The first application we're going to talk about is analysis of recycled plastic resins. When we have a plastic material, the first question most people would ask is, what is this material? So both FTIR and Raman can be readily used to characterize the major composition of different types of polymer materials. In addition, Raman can be very helpful to look at degradations in polymer resins. So here I have an example showing the Raman data obtained from a degraded polyethylene resin as well as a virgin polyethylene resin. So by comparison, you can see very distinct differences in the Raman data. For the degraded polymer resin, typically in the Raman analysis, a broadband fluorescence was detected, especially in the resin that are thermally degraded. This is because the polymer chains will break down and creating hydrogen defects in a carbon matrix, which further leads to strong fluorescence in Raman analysis. Raman is especially sensitive to this type of fluorescence, so Raman can effectively detect thermal degradation in polymer resins. Aside from Raman, we have complementary techniques, including GPC, which can be used to characterize the molecular weight of the polymer resins, as well as TGA, which can be used to study the thermal stability. So all those different techniques provide useful insight into the degradation in polymer resins. So another common area of interest in recycled plastic analysis is the determination of impurities. My colleague Janica worked on a very interesting project to study recycled ABS resins. So FTIR analysis was performed on ABS resins that has gone through an increased number of recycling process. So by comparing their FTIR spectrum, the overall similarity in spectrum profile suggests that there's no major change in the composition between the recycled resins and the virgin resin. And then a closer comparison of the fingerprint region reveals minor changes in the relative intensities of the peaks at 1760 and 1728, which may be indicative of changes in the low-level impurities and additives in the recycled plastics. Aside from FTIR, we also have GCMS, which is a very useful technique to quantify low-level additives in polymer resins, and also XRF, which is an elemental technique, provides excellent detection of metal impurities with excellent detection limit, which it can go down to ppm or even ppb level. So all the aforementioned techniques are readily available at EAG, and we actually have a full suite of techniques that can be utilized to study polymer materials. Now moving on to case studies that are more specific for Raman. We received a question asking if we have any experience using UV Raman to study DLC materials. The answer is yes. So here first, DLC stands for diamond-like carbon. And I want to mention here that Raman is the most powerful technique to characterize and distinguish between different allotropic forms of carbons, including graphite, nanographite, DLC, diamond, carbon nanotubes, as well as C60. So specifically for DLC analysis, the Raman data obtained from the DLC sample can be band-fitted to further deconvolute the characteristic D and G bands of elemental carbon. By using the peak ratio of the D and the G bands together with an empirical equation, it is feasible to estimate the sp3 content in the DLC films, which is a very important indicator for the quality of the DLC product. Another very useful application for Raman is to characterize the stress and strain in semiconductor materials. The example I have here is a thin silicon ap layer that was grown on a silicon germanium substrate. And due to the lattice mismatch, stress has been created in the ap layer, and Raman can be utilized to study the level of stress. So here we have the Raman spectrum obtained from the sample, which is a blue trace here, and we also have a Raman spectrum obtained from a stress-free silicon sample, which is a red curve here. So zooming in on this silicon peak as shown here, we detected a strong peak at around 500, corresponding to the silicon vibration from the substrate. And on top of that, there is a shoulder peak at around 511, corresponding to the silicon vibration from the ap layer. By comparison to the characteristic silicon peak from a stress-free sample, which is typically located at around 520, a huge redshift has been detected. And the redshift is actually proportional to the magnitude of the tensile stress in the silicon ap layer. By using equations reported in the literature, we can convert the peak shift in Raman to calculate the amount of stress in the layer. Stress analysis can be performed at specific locations, or it can be performed in a mapping mode, which provides data to show the distribution of the stress throughout your device. Speaking of the mapping capabilities for Raman, I have one last case study highlighting the Raman capability, the mapping as well as the confocal capabilities for Raman analysis. The sample we have here is a pharmaceutical cream, which contains two different types of active ingredients, which we simply call API-A and API-B. So first, Raman analysis was performed on the pure form of those APIs, and the unique peaks in the Raman spectrum of each API can be utilized as signature for further mapping studies. Due to the confocal capability of the Raman microscope, it is possible to focus the laser beam down into your sample at a defined depth and obtain the Raman signal just from the focal plane, which is theoretically 1 micron thick. So here I have two maps This one was obtained from a depth around 40 micron, and this one was obtained from a depth around 70 micron. So in the 2D maps, the red regions highlights the agglomeration of API A, whereas the green regions highlights the agglomeration of API B. Although being very time consuming, it is possible to perform the mapping analysis in 3D mode, which gives the even better visualization of the distribution of the APIs. So with that, I would like to conclude my presentation, and I want to emphasize again, both FTIR and Raman have very strong capabilities to characterize a wide range of material that can be used in a wide range of industries. So if you have any specific analytical questions or analytical needs, feel free to reach out. We are here to help. Now, without further ado, I would like to hand over the presentation to my colleague Victor, who's going to discuss a very exciting new technique called NanoIR. All right.
Thank you for that, Wenchong. So we are moving on to the third and final technique discussed in this webinar, NanoIR, which is one of the newest tools that we have acquired here at EAG. And there were a lot of questions that were submitted regarding NanoIR, how it works, and its specific applications. Way too much to get through in a section in this webinar, so we'll get to those questions more in depth in follow-up emails. So there were a lot of questions coming in just asking what is the technique, how does it work, what is it capable of? So I just wanted to take a quick minute or two to describe what it's comprised of and its bare working principles. So the technique itself is a AFM-IR based technique, that is atomic force microscopy and infrared spectroscopy based technique, where we sort of combine the best of both of the techniques. So we get the spatial resolution and topographical and mechanical information from AFM and the chemical information from infrared spectroscopy. So we're able to collect all of these at roughly 30 nanometer spatial resolution. And the bare working principle of it is that we have the AFM cantilever positioned on the sample at a specific region of interest. We irradiate the sample with our infrared laser at a fixed frequency, and then we measure the sample response, whether or not it absorbs the infrared light. And that response should induce a force on the cantilever that we can measure. And if we are sweeping the laser frequency at a fixed cantilever position, we're able to measure the response of this as a function of frequency, which in turn regenerates the infrared spectrum. But because we're local to the AFM cantilever, we're collecting these at nanoscale level resolution. Alternatively, if we are fixing the frequency at a specific functional group of interest and just sweep across the AFM image region, we're able to generate chemical maps. So these sort of show the distribution of the compounds across the sample spatially. So the general workflow, or how we generate this data, is that we use the optical microscope on the instrument to relocate or find a region of interest, and then we collect an AFM image of the sample. And then we're able to specify specific locations to park the AFM probe at, which then help generate, or which then we collect the NanoIR spectra upon. And from there, there's sort of two different things that we can do. One is if we notice heterogeneities across the sample, we can chemically map out specific functional groups. In this case, we're mapping out nylon across this image region, where the blue is the absent region and the red and the yellow are regions of this sample that are enriched in nylon. And we can also bring this back to our extensive FTIR libraries and perform library matching to identify what compounds are comprised in the spectra. So typically, you're going to get 3 sets of data from NanoIR, and you can imagine different scenarios in which you can apply these. So the images from AFM, such as height images, give you insight into what the sample looks like. Chemical maps, which again are fixed frequencies for specific functional groups, tell you how compounds are distributed across your sample. And the spectra themselves are really useful if you want to figure out, well, what is my sample made of? And there's a lot of different, applications, many more than what I have listed here, but a couple of examples are sidewalls or pattern materials, cross sections of polymers or polymers mixed with inorganics, as well as small particles and contaminants that are all on spatial resolutions or scales that you can't access with, say, Raman or with FTIR, because the spot size of those is so much larger than the sample or feature of interest. So in terms of the instrument itself, the NanoIR we have is a Brooker dimension icon IR. And we got a question about, how do we handle water absorption in this infrared region, because that also contributes to the background or signal. And the answer to that is we purge it with nitrogen, which has no infrared active modes, and we get it to roughly 1 to 5% relative humidity. And then we operate the instrument in two main modes. One is contact, in which case the cantilever is deflected from the surface upon infrared absorbance. And this has the closest correlation with FTIR, but relatively high lateral forces, which can be destructive if you're working with materials that are too soft or too loosely adhered, like liquid or oil droplets. The other mode we have is tapping, where you oscillate the cantilever and it intermittently touches your sample. So it's much less destructive. And the signal we're detecting in this case is how the oscillation of the cantilever is altered as the sample absorbs the infrared light. And this is much better suited for if you're working with soft or very loosely adhered materials that might be destroyed or dislodged in contact mode. In terms of what we can cover, the spatial range, the spectral range, and those aspects of the technique, we're really looking down to 30 nanometers or less in terms of feature size. And you can sort of visually see that in the figure to the right here, where you can see how much smaller the spot size of NanoIR is relative to both Raman and that of FTIR. But because we're using tunable lasers, we're really confined to the technology that is in place commercially in that field. So we have two separate lasers that span the range of 4020 to 2680. This covers your CH, OH, and NH stretches, and that we work with a spectral resolution of roughly 4 wave numbers. And then to cover the fingerprint region, we have a QCL laser, or a quantum cascade laser, that covers 1860 to 751, and we have a resolution of 1 wave number. So there's a middle gap around 2680 to 1860 that has a couple of functional groups that we just don't have access to. These include nitriles, silicon hydrogen bonds and silanes, and C triple bond C alkyne materials, as well as most inorganics that occur below a 751 wave number. In terms of calibrating the instrument, we have two sets of calibrations. One is for the AFM, in which case we use gratings for the X, Y, and the Z aspects of it. And then for the IR laser itself, we make sure that the wave numbers are accurate using a polystyrene calibration. So in terms of sample prep and the type of information that you want to extract with this technique, there's sort of two ways that you can look at this. One is if you're looking at surface coverage. So if you have a coating on top of a film or another structure and you want to map out, how much coverage it is, we just have to load the sample as is into the instrument, and we can map out, how much of your surface is covered with this coating, or how heterogeneous is this coverage. But if you really want to get quantitative information on how thick this coating is, whether that's through just AFM imaging itself or through mapping out how much region is absorbing a certain functional group that corresponds to your coating, then we would want to prepare a cross-section by either embedding that in an epoxy matrix if it's at the very edge of your sample, or if it's a multi-layer stack and it's within that stack, we can just cross-section it as is. Another question we got that's actually fairly interesting is, will this technique work with a tiny particle on a membrane? And more generally speaking, if your sample is on an infrared active substrate, so in this case, I have an example of polystyrene on a silicon wafer, which is fairly IR inactive, versus glass, we can see that in the blue, which is the polystyrene on glass, there are absorbances that are due to the underlying substrate. So if there are unique peaks that we can pick out that don't show up in your substrate, the chances of us succeeding are higher. But ideally, we would want, the Z profile of it to be on something that is IR inactive, so that we could best isolate those peaks to your material of interest. In terms of sample size, the restrictions that we can physically fit into our instrument, obviously the smoother the sample, the better for AFM. But in terms of how much we can image, we can do roughly 60 by 60 microns with a maximum height tolerance of around 10 microns. And then more macroscopically, we have roughly 150 millimeter scanning stage. So that's roughly the largest we can fit. We can offset it a bit if you need larger samples. And then the tallest height we can tolerate is roughly 18 millimeters. And the sample itself can't be too heavy. So ideally less than 454 grams or 1 pound. So how does this technique really compare, or rather taking a step back, how does vibrational spectroscopy compare with other analytical tools that you might find or use here at EAG? And the best way to answer that is that we're really looking at bonds and whole molecules of organic components. So other techniques might give you insight on the elements that are present in your sample, and the inorganics, or rather some techniques might give molecular fragments or states, but we're really giving you insight into specific compounds or class of compounds using vibrational spectroscopy. So if you want to nail down, exactly what type of polymer or the closest class of polymer is in this material, vibrational spectroscopy is one of the strongest methods that you can use for that. And then in terms of comparing, imaging capabilities with other elemental ones, the main advantage of these vibrational spectroscopy imaging modes, so that's Raman and NanoIR, is that we're giving you insight into the functional groups and how they're distributed on fairly high spatial resolutions. So you can get information such as where the carbon and oxygen is through EDS, but you're not going to be able to tell what that carbon or oxygen is bound to, or what specific compounds it might be correlated back to. So this is really where the vibrational spectroscopies shine. And lastly, I wanted to take a step back to sort of give another overview or comparison of the three techniques. And here I have a table on the right showing some of the main parameters that you might be looking at. And the highlighted regions are sort of where each technique shines. So if you want spectral range towards the higher wave number, which include the OH and NH function groups, you might lean towards FTIR. Whereas if you want inorganics, we want to take advantage of the low wave number capabilities of Raman. The probing depth, it's obviously very material dependent, but this is where NanoIR and FTIR shine, is that we have much more capability to sort of tune it. In terms of spot size, NanoIR outclasses the other two by far, where we're able to access, sub 30 nanometer spatial resolution. But if you really want to do analyses that also include inorganics or are the least destructive, then you might lean towards, say, Raman. But the main thing we want to highlight here is that all three of these techniques, because we have extensive libraries for compound matching and identification, all three of these vibrational spectroscopy techniques are great if you want to identify exactly what organic compounds are present in your sample. And with that, I want to bring back all of the other panelists, and we will begin the Q&A section of the webinar.
All right, thank you so much, Victor. That was really interesting. Okay, so we have received a lot of questions. I did my best to answer them in real time, but we will get to all your questions, rest assured. Okay, so Wencheng, I have a question for you.
Sure.
Is it possible to accurately quantify antioxidants in a polymeric system that contains 3 or more oxidants? Very specific question.
Yeah, well, I would say the general answer to this question is yes. If you are thinking about just using vibrational spectroscopic techniques to do that, it could be very challenging. We have successfully utilized FTIR to detect antioxidants in polymers, and it worked really well if we're just doing a solvent extraction to try to get the antioxidants out and then try to identify them. See, if we get all the antioxidants extracted and then we try to quantify them, that's where FTIR can get a little bit tricky. FTIR typically is not quantitative. It will require external standards in order to do quantitative analysis. And in a mixture of like more than 3 antioxidants, we have like a limitation with detection limit. But if we're just generally speaking, if we want to try to quantify antioxidants, we have other more straightforward, more effective techniques, including GCMS. We have successfully utilized GCMS, which stands for gas chromatography mass spectrometry, to quantify different types of antioxidants like the sterically hindered phenols in the polymers. Or if the antioxidants of interest is too high boiling and doesn't really fly in the GC, we have liquid chromatography mass spectrometry LCMS that can also be utilized to do that. And both of those 2 techniques offer much better detection limit compared to FTIR. Yanka, you are muted.
Sorry about that. Thank you. It's a great answer. We have another interesting question, and it is asking if FTIR Raman can be used for polymer sequence determination. So I will answer that one, and that is going to be very challenging. It is possible. It depends on the polymer molecular weight, depends on a variety of issues. If the polymer sequences have different spectra, then yes, that's possible, but it's a challenging kind of analysis for vibrational spectroscopy. Perhaps pyrolysis GCMS might be better, or NMR or something like that. Okay, so the next question I have is going to be for Victor, and the question is, according to you, does NanoIR have acceptable repeatability for characterization of organic layers on an inorganic material? So repeatability of NanoIR.
So this is actually a really interesting question, because you have sort of 3 factors that account for the signal. One is the laser source, which is fairly constant, at least in my experience, the sample itself, and then assuming the sample itself is the same between measurements, then you're typically restricted to variability in the AFM cantilever. So we've noticed that between cantilevers or batches of cantilevers, there is some variability in the overall signal that you get. So that is the absolute intensity, but the actual spectrum themselves, the shapes and the relative peak intensities between them are fairly consistent between measurements.
Thank you. And a quick follow-up to that, which is how flat should the surface be for NanoIR? You know, what kind of surface roughness can you live with?
I would say ideally we would want height steps or maximum of 5 or so microns. If it's too tall, then you can imagine that it might attenuate or block the IR from reaching certain features in your sample. But of course, with these AFM-based techniques, the flatter you can get the sample for this, the better. And we have a lot of service lines that are dedicated towards sample prep or polishing if needed.
Wonderful, thank you. Okay, Wenchong, I have a question for you, and that is going to be, are you able to use FTIR and/or Raman to detect surface defects?
I would say the general answer to this question is yes, absolutely. More specifically, I mean, when talking about surface defects, there can be many different types of defects. A lot of the cases we see the defects as like a foreign material or a stain or a residue, something like that. Then that's where FTIR, Raman, or even NanoIR, depending on the size of the defect, that we can use those vibrational spectroscopy techniques to try to identify the composition of those defects and then help you to trace back to its source. There are also circumstances where something shows up as a defect, but when we try to analyze it, it turns out to be the same type of material. Those are actually can be just mechanical artifacts on your sample, and we have imaging techniques such as optical or SEM imaging that can further help to characterize those type of defects. So it really depends on the actual type of defects that you are looking at, and then we have a full suite of techniques that can be used, utilized to study that.
Thank you. It's a great answer. I have a question here, whether we can use these techniques for deformulation, and I'd like to answer that one. Absolutely. These are great techniques, especially if you don't know what something is. This combined with an elemental technique is one of the best tools for figuring out what it's made out of. Because with FTIR, with Raman, we have these libraries. We can characterize unknown materials. So it's the same principle as what is the defect? It's just, what is the material made out of? Okay, I have another question for Victor. According to you, does NanoIR have acceptable? Okay, so that's very similar. What are the physical limitations of NanoIR versus IR? So physical limitations for samples.
So physically, we are much more limited to smaller size samples because we can only accommodate, a max height of like 18 millimeters. And FTIR can work with samples that are naturally much rougher because we can operate it in transition mode. So if your sample is too rough or too large, for NanoIR, we likely have to do additional cut or prep work to get it to fit into the instrument.
Okay, I have a question for you now, Wenchong. It's a pretty technical question about ATR versus transmission. So compare ATR versus transmission peak intensities of the same material. How do the increased detection limit in ATR, including path length, affect the result?
Okay, I guess there are two questions in this one. First, comparing the peak intensities in the ATR and the transmission spectrum for the same material. So actually, the intensities, especially for peaks towards the low frequency range, so towards the end of the spectrum, one typically see very different peak intensities. In the ATR spectrum, the peaks in that range tends to be much stronger compared to the same peaks in the transmission spectrum. This is because in ATR analysis, the penetration depth is actually dependent on the frequency or the wavelength of the light. The lower the frequency means the longer the wavelength of the light, and then the penetration is deeper. With the deeper penetration depth, you will get more signal, and that is why towards the low frequency range of the spectrum, in ATR analysis, the peaks tends to get enhanced. And the other question asking about how to increase like the path length or sensitivity for ATR analysis, I could think of like two general methods. First is to use a multi-bounce or multi-reflection ATR, where the infrared light bounces multiple times through your sample. That will help to effectively increase the path length compared to just a single bounce ATR. Or alternatively, we actually have a very powerful tool, which is called grazing angle ATR attachment in our lab. By using this attachment, you can increase the incident angle from like typically 45 degrees for most ATR attachment to as high as 65 degrees. And this grazing angle incidence really helps to achieve much higher sensitivity. And grazing angle ATR actually works pretty well to characterize like really thin films or surface modifications. So yeah.
Wow, that's a great answer. Thank you. Okay, we have one more question. How do I know if Raman or FTIR laser is destroying my organic samples? Can I tell by just looking at the spectrum?
I would say yes, both the spectrum and the appearance in the camera, right? For FTIR, we don't really, I would say we have never seen that a sample get destroyed by exposure to infrared light because it's a very mild, low power source. When it comes to Raman analysis, depending on the laser, because the laser does have much higher energy, there is a chance you may be able to burn your sample if you use too high of a power level. we always like optically inspect the area for analysis before and after collection of the Raman spectrum. If the sample gets burned, you may see changes, like the sample may get dark in the physical appearance. That's a sign that tells you your sample may get degraded. Or in the spectrum, if you are really burning your sample, you may see carbon peaks or fluorescence that's starting to show up in your spectrum, which is a sign for you to tell, okay, I use too high of a power. I really need to reduce my power.
Wonderful. Okay, well, thank you so much. This is all the time we have for questions. I just want to end with why choose EAG? You know, we really care about confidentiality. That's a core to our business. We have wonderful scientists with years of experience. We have 2,500 instruments, all within one company, and we are basically a global leader in material science testing. So we love to solve your problems. You don't need to know what technique to use. You can just reach out to us.
So just wanted to say thank you to all of our experts for this robust discussion and presentation. And thank you to everyone for attending today's event. If we didn't get to your questions today, we'll be following up with you soon. And if you have any other questions, please send in your questions to the email address on the screen. That's customerservice@eurofins.eag.com. Also want to mention that I've added a few links to our resources in the chat window, so please check those out. And once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate your feedback. On behalf of Eurofins EAG Laboratories and our experts, thank you for joining us today, and have a great rest of your day.
Bye.